Um, Today we said that we were going to discuss a bit about the force on current carrying wire in a magnetic field. Uh, you know, magnetic fields, we have seen them with bar magnets and other permanent magnets. But permanent magnets are not the only things that produce magnetic fields. Electric currents produce magnetic fields as well. In fact, it's the same type of field because the magnetic fields produced by bar magnets are produced actually by tiny little currents of the electrons inside the material of the bar magnet. So it's actually the same thing. So strictly speaking, we can say in general that magnetic fields are produced by electric currents. They're also produced by changing electric fields, but we are not going to go there now. So anyway, so we see that electricity links very, very closely to magnetism. It's like two different faces of a coin, but they are not the same thing though. So anyway, so considering that an electric current then produces a magnetic field, and here in this picture shows the shape, help us to see the shape of the magnetic field produced around the current carrying wire. So I hope you can see these long rods here. This supposed to be current carrying wire. It's a wire with a current, and the current on the right hand side is up. Its direction is up. And we see that if we have a number of magnetic compasses all around this wire, we place them around the wire, we see how they align. They align and they form a circle. In fact, let me tell you this. I have had made a video on that, but it's not edited, so I don't want to leave the voice there. But you see, this red thing here, this red thing is it's a piece of wire with a current. Well, when it is connected to a circuit, there is current there, but when it's not connected to, if the circuit is not complete, you see the magnetic compasses point to the north. Sorry, let me remove the voice because it drives me crazy and I can't concentrate. You see now, as it is, if you look at these magnetic compasses, which are little bar magnets, of course, they point to the north, where the geographic north is. But if we connect now this piece of wire to the battery, and there's current in the wire, we'll see that these magnetic compasses will align and will point as if they form a circle. So now let me find out where, here it is. Okay. Here it's not connected, and then when it's connected, you see that they change direction. Here it is not connected, and come on, connect it. Yeah, there, yeah. When now you see when they move, and you see that they move and they align, the compass needles, they align roughly in a circle. And look at the direction of this circle is the direction of these little compass needles. And later on, somewhere I draw this little circle around the compass needles. And okay, that's enough. This is a terrible video because it needs editing. That's enough. I just wanted you to see that the compass needles move, and it happens in real life. It's not only in the pictures that we see in the book. So we see now here that we can scribble on the page here. You see, in this case, where the current in this wire is up, we see how the magnetic compasses align and they form a circle. In this case, it's like counterclockwise, which shows that there is a magnetic field produced around the current carrying wire, and it's there when there is a current in the wire. And there is a rule to find this magnetic field, the direction of the magnetic field, by using a right-hand rule. There it's the right-hand rule, in which case, you see, if we grab with our right hand the piece of wire, with our thumb, here's our thumb, pointing to the direction of the current in the wire, then our fingers curl around the wire in the direction in which the magnetic field curls. And it would be nice if I knew if you have read this chapter in the book, if you have been in this electromagnetic, which chapter is that? I don't know. Chapter 20, electromagnetic forces. Yeah, chapter 20. I don't know if you have been there in the book. It would be much better, because then you would know what you would have seen this rule before. Anyway, so there is a right-hand rule to find the direction of the magnetic field lines around a current carrying wire. And now, this being said, we see that the current carrying wire, since it produces a magnetic field, acts like a magnet, really. And since it is a magnet, produces a magnetic field, we would expect it to interact with other magnetic fields. And there is where we come to the topic of the force that the current carrying wire experiences in a magnetic field. I mean, it is reasonable to expect that the current carrying wire will experience a force inside another magnetic field, because if it is a magnet itself, obviously it interacts with other magnetic fields, isn't it? So that is why it experiences a force in a magnetic field. So here we have the case that we were discussing we came across last week. We were not discussing it really. So we have, this picture shows a piece of wire, again, a current carrying wire, which means it is obviously, this is connected to a circuit, say to some battery, with this being the positive, this part of the wire connected to the positive terminal of the battery and the other side to the negative. How do I know the polarity of the source that is connected? Because we can see the current. Look at this arrow here. It shows the direction of the current in the wire. And we know that the wire, the current in an electric circuit has a direction from the positive to the negative terminal. That is the direction of the current. So that is why I know that this wire has to be connected in this way to a battery here. Okay, so when this piece of wire now is placed inside the magnetic field, where is the magnetic field? It is produced by these two magnets here. Here we see a north pole, and here we see a south pole. And in between those two poles, the magnetic field, we'll assume it is a uniform magnetic field. And these blue lines here with these little arrows show the direction of the magnetic field in between those two magnetic poles. So according to what we said now, considering that this current carrying wire behaves like a magnet because it produces its own magnetic field, obviously it will interact with an external magnetic field. This is the external magnetic field produced by those two poles, which we don't know where it comes from. Perhaps these are the ends of a huge horseshoe magnet, perhaps. Doesn't matter. It doesn't matter as long as we have a magnetic field. So we see now, we have in this particular picture, the magnetic field is from north to south, that is from left to right, with its direction. We have also the current here in the wire, which is from the positive to the negative terminal. And note that this wire is, in this picture, is actually perpendicular to the magnetic field, isn't it? And this wire now will experience a force, and this force is a third kind of vector in this case. And well, they show us the force that this current carrying wire will experience, and here is this orange little arrow represents the direction of the force. So we have like three vector-like quantities. We have the magnetic field, which is a vector. we have the current, which is not really a vector, but it has a direction, so we treat it like a vector. And we have the force, so we have like three vector-like quantities, all perpendicular to one another. And this makes it very, very hard to draw it on a flat piece of paper, isn't it? How do we draw three vectors perpendicular to one another in 3D on a flat piece of paper? So as you can see, there is a necessity to introduce some new kind of symbolism, some new kind of representation to show these three vector-like quantities. But before we get there, there is a rule, a trick that we can use to find the direction of the force that this wire will experience. And in your case, in the IG course, this trick is given by Fleming's left-hand rule, which is represented here. Here is this trick that we can use. It's another hand rule that we can use to find the direction of the force in that the current carrying wire experience inside the magnetic field. And it's important to say Fleming's left-hand rule. It's also important to say Fleming's left-hand rule because there are quite a few hand rules to find these directions. In fact, to find the same direction, we can also use some other right-hand rules as well, but you don't need to know all these rules. You just need to know one rule, which is in your book as well, which is called the Fleming's left-hand rule. And in this hand rule, we use these three fingers, the thumb, the index, and the middle finger, and we place them perpendicularly to one another. And as you can see, okay, in your book, it's in page 286. In page 286 in your book, the thumb, they call it, they say here thumb, but the M, the two last letters, they have especially the M capital, because the M of the word thumb represents the motion. When they say motion, they mean the motion of the current carrying wire. It will move, in which direction it will move, they mean. The index finger, they call it the first finger. They say first finger with the F capital, finger, because the F represents the field. And the middle finger, they call it here the second finger, and they use the C of the word second as capital, second finger, because the C represents the current. So if you want to remember these three fingers in terms of the thumb and the finger and the second with the C the capital C, to remind you that this is the current, it's fine with me. It's up to you which one helps you the most. But me personally, I find this very confusing, and it's not very helpful for me. I remember when I was small, and I still, now that I'm so old, I use rather I call these fingers FBI because it reminds me of the FBI, the Federal Bureau of Investigations, you know, from the movies. FBI, it's easy to remember. And the fingers appear in the same order, FBI. The thumb is the F, which means the force. The next finger is the field, because the field actually has a symbol, and it's symbolized by B. The magnetic field is symbolized by B. That is why the B stands for the F, the second letter of the FBI. And the I, of course, is the current, because for current we use the symbol I to symbolize current. And the first is F, because we use the symbol F to symbolize the force. So this is force, field, current. These are the actual symbols that we use in physics for the force, the field, the magnetic field, not the electric field, the magnetic field, and the I. So it's easy to remember, FBI. So I prefer this kind of wording to remind me which finger is which. I don't know, but it's up to you. As I say, you can use thumb, first finger, or second finger, or you can use FBI. It's up to you. I don't want to shove it down your throat, just because my favorite is the FBI. Anyway, so we need, so hold it now. Let's stop sharing here, because I need. So you see, the problem with this picture that you see now is that I'm holding here my left hand, but you see it as my right hand. That is why I don't want to show you with my hand as we move along in this session, because you see the mirror image of what I'm showing you. So let us go back to our videos and so on. Which reminds me, hold it, I had the video somewhere. Let me find the video. Let me show you the video. What a minute. Let's bring all that here. I hope you can see this video now. Send me a message if you cannot see it clearly, okay? Let's see this one. Let's watch it.
Hopefully you remember that around all magnets, often 5-minute physics. This video is about the motor effect, how we can predict the force on a wire in a magnetic field. Hopefully you remember that around all magnets we have a magnetic field, and we can show that magnetic field by drawing magnetic flux lines, which always go from a north pole to a south pole. Those are the white lines on this diagram. Now imagine we have a wire going through that magnetic field. At GCSE, the wire is always going to be perpendicular to the flux lines at 90 degrees. And if we put a current through that wire, going from positive to negative, you can see the direction as the arrow on this wire, then that wire is going to experience force. And that means that the wire is going to move. Now this effect is really important. We use it in loads and loads of different devices. It's called the motor effect. But how did I know that the wire was going to move upwards? Why not down or to the right? Well, to work out and predict the direction, we use something called Fleming's left-hand rule. Fleming's left-hand rule uses, surprise, surprise, your left hand. And what you need to do is make this shape with your left hand. Point your index finger forward, stick your second finger across, and point your thumb upward. And each of your fingers represents a different thing. So then the first finger, the index finger, represents the magnetic field going from north to south. The second finger represents the direction of current going from positive to negative. And your thumb is going to point in the direction of movement, the direction that the wire is going to experience force. Now, in any question you are given, you're always going to know two of these three things. So all you have to do is line up the two things that you know with your hand and see which direction the other finger or thumb is pointing. And normally we get given a field and we get given a current, and we have to predict the direction of the force, the direction of the movement. So let's see this in action. Here we've got the setup we had before. We have our field lines going from left to right, and we have our current from out of the page. So if I put my hand in the right place and line up the fingers with the field lines and with the current, and my thumb points upwards, and lo and behold, it predicts what we saw earlier. The wire is going to move vertically up. What about a different situation? Let's try this one. Why don't you pause the video and we'll see if you can work this out. Okay, so here's my left hand again. I'm going to put my first finger along field lines, going from left to right. My second finger is now pointing down, so I've rotated my hand around, following the direction of the current. That means my thumb is now pointing out of the screen towards us. So the wire is going to experience the force out of the screen, and it's going to move towards us. If you have this in an exam, you would literally write out of the paper or out of the page. couple of common mistakes people make with this. Number one, it's called Fleming's left-hand rule. It doesn't work with the right hand. Just make sure you are using the correct hand. Secondly, you can move the paper around on your desk. You don't have to keep the paper still. Otherwise, you end up dislocating wrists, pulling shoulders out of joint. It's really not worth it. Just think about rotating the paper a little bit. It does make your life a lot easier. So we've got to think about another way of representing this. 3D diagrams are all well and good, but sometimes they will show the direction of the current in a slightly different way. Imagine this situation here. We've got a dartboard, we can throw a dart at it. And imagine you, unfortunately, have to be standing with the dart coming towards you. What you'd see as it came your way is predominantly that point of the dart and a little grip around it. So that represents something coming towards you. If the dart was going away from you, you'd see the flights and that sort of crosshair pattern. So these two symbols are sometimes used in diagrams to represent the wire with the current. And this tells us whether the current is going into the page or out of the page. On the left-hand side, that current is coming out of the page towards us. On the right-hand side, the crosshair means that the current is going into the page away from us. So just see what this looks like in action. There we have it. So just, again, use your left-hand rule, see if you can work out which direction it's going to move. So your second finger should be pointing out of the page towards you. Your first finger should be pointing down, going with the field lines north to south. And that means, of course, that the wire is going to move to the right. Well done, you got that correct. So to summarise, the wire that's carrying current will experience a force as it moves through a magnetic field. It's worth knowing that at GCSE, the wire and the magnetic field are always going to be at right angles to each other. And the direction of that force can be predicted using Fleming's left-hand rule. Thanks for watching this 5-minute physics video. Please subscribe or check out our other videos teaching GCSE Physics. Simple.
Okay. I hope you saw it, and I hope you could hear it. All right. So here we are with the right-hand rule. Now I want you to see, I want to show you another video that shows this force on the current carrying wire as well, real wire. If I find it, sorry. Okay. Between those two springs, a very light wire, which we are going to cut from aluminium foil, like normal aluminium foil that we use at home. And we are going to place this wire inside the magnetic field. So first, let us see how to make this wire. What we need is take a flat piece of aluminum foil and cut a thin strip like a couple of millimeters thick, if we can, carefully. And we must be careful not to crumble this aluminum foil. We need to keep it flat and nice. Why do we use this foil? Because it's very flexible and light, and we can see an effect if it moves up or down or in any other direction. If we use any other piece of wire, copper wire, it's quite rigid in comparison, relatively rigid, and it does not move so well. Okay. So here is our foil. We are going to connect it to our springs, a bit high on the spring so that we leave space below and above. So first we connect one end, and then we connect on the other side. We must not stretch it. We must leave it a bit loose so that we see how it moves. So there is the other part. All right. So this will be our wire, and of course this way we are going to connect it across a battery, but not yet. When we are ready. Now we need a magnetic field because this current carrying wire must be inside the magnetic field to experience the force. So what do we have here? We have two Magnadur magnets, which, as you can see, are quite strong magnets. They don't separate easily. We have a north and a south pole. I have marked them on a tape because the Magnadur magnets do not say which side is the north and which one is the south. These are very common magnets when we do electromagnetism experiment. So you see, north and south, they attract one another. So we are going to place a north and a south at some distance away, across like that. But because these two sides attract one another, we need to put a couple of strings there to keep them apart. Otherwise, they will join, and we don't want them to join. We want to use the magnetic field in between them. So remember, north and south is, they will stand up behind the springs. The springs keep them apart. So now we can connect our battery. Let's connect first one side, and with the other side we'll touch the other end of the wire. So we'll have a current in the wire. Now we need to understand here some directions, because we have a magnetic field, we have a current in the wire, and we're going to have a force acting on the wire. We expect to see a force. We expect to see actually the wire moving in some direction depending on the force that it experiences from the magnetic field. We need to remind ourselves what is the direction of the magnetic field? It's from north to south. So here there is a direction of the field from north to south in this direction. If I connect my battery in this direction, look at this. This is the red lead, which means this red lead starts from the positive terminal of the battery, and this is the negative terminal of the battery, which means the direction of the current will be from red to black. So the direction of the current will be toward me. We need to remember those directions. And now let us touch the wire, and let's see what you see. It's pushed up. Let's see it again. It's pushed up. You see it in this direction. Let's see it again. Pushed up. So it experiences an upward force. Let us apply the right-hand rule here. And see Okay, no, that's enough here. That's enough from this, because you know why? Because I'm using a different right hand, a different rule, not Fleming's left hand rule. So what's that? Okay. So I hope you saw the wire moving up. Of course, if we were to change the direction of the battery, the way we have connected the leads, red and black, we change them, we connect the opposite ends, the aluminum foil would go down, and we could also change the position of the two magnets, north and south, and it would also change direction for the force. Now, okay, so that there's no time again, but another interesting thing that we saw in the YouTube video actually was when they introduced these symbols for having vectors into the page and outside of the page. And remember that there was a dot for when the vector comes out of the page towards our eye, and there was this sign X if a vector goes into the page and away from our eye. Why? Because it comes, this symbolism comes from an arrow, because if we look at an arrow and if we have our eye there in front of its tip, we're going to see this shape. This is the tip of the arrow, and this round thing is all this round thing around the point of the arrow. But if we place our eye at the back of the arrow and we see those feathers, what we actually see is this X, that the feathers kind of the shape of the feathers. Here you can see it actually better. If we have our eye here at the behind the arrow, we're going to see an X. If we have our eye in front of the tip, we're going to see this symbol. I hope you understand these symbols, where they come from. Pretend it's an arrow that moves into the page or out of the page here.